This video explains the process of creating an application out of your Python code that you can run on APEER.com, which is a cloud-based image processing platform for microscopy applications. Of course, the starting point or a prerequisite is that you have a working Python code that you would like to create an application out of. So for this tutorial, let's actually write a few lines of code in Python. And in fact, let's copy a few lines of code from scikit image non-local means denoising documentation online. And if you scroll down, you can see that I'm going to copy the header, and they have various implementations. They have slow algorithm, they have fast, and which is basically different lines of code. So I'm just going to copy this one line for slow algorithm, where the input parameters include sigma estimated, which is again this line, which means I'm going to copy that line, and of course all of these other parameters that actually go into in here. So I've already done that, and again here is the code in my Spider IDE. You can see that I have my headers up there, importing the required libraries, and I'm going to work on a single image called Mona Lisa noisy.jpg, and that is in the same folder right here. And this is the image that we are going to denoise, and the sigma estimated, and of course this is the primary piece of code that's going to apply this non-local means denoising to this input image, and it's going to save it as nlm.jpg. Okay, so let's go ahead and run this to see that the code is actually working as Python code. Okay, so that's a great sign. Everything worked fine. And if I go ahead and look at the my directory, so now I have another image. Instead of opening the images, let me actually increase the size of this. So now you can see I have my original input image as the noisy.jpg, and now I have my output image that's actually a cleaned version of this input image. So the code is working fine. We are all set to create a module or an APEER module out of this, which is nothing but a Docker container where all the dependencies are within this Docker container. So let's go ahead and get started. So now let's get back to our APEER.com right there, workspace. Go ahead and log in and sign up. Obviously, if you haven't signed up yet, go ahead and log in, and you should see a screen that I'm very similar to what I'm seeing here. And in fact, if you are logging in for the first time under my modules, you probably see 0. In fact, I created a new account here. Let me open another screen where you see under my modules, it says nothing. This is how it should be on your screen if this is the first time you ever logged on or tried to create a module. Now, we do have some text here that actually talks about how to create this module, how to get started. Obviously, step number 1, of course, prerequisite number 1, I should say, is you got to have your favorite IDE installed, which is again your integrated development environment, like Visual Studio Code, for example. In my case, I am using Spider, which is part of Anaconda distribution. Go ahead and install Git. I'm working on a Windows system, so I installed Git for Windows. And Git is used to manage your code, to push and pull the code off the platform. And how do you do that? Using your Git credentials. So if this is your first time, go ahead and provide a username and password. You can pick any username and any password. That's up to you, and you can change it anytime you want. Okay, and then we can go ahead and start creating the new modules. Fine. So once you're done with that, of course, with those steps, what you should see is a screen like this, and of course without any of these additional modules. So again, the way you create your module is obviously click on add new module here, give it a name. Since we are trying to create a non-local means denoising filter, let's just give it a name, calling NLM denoising. And here you can actually select one of the 6 or 7 templates, actually 5, 6, 7 templates that are present here. One, you can start with an empty module, which means you know what you're doing. You don't need any cookie cutter templates. You can write your own Docker file. You can write everything. I really do not recommend that, even if you know a lot about Dockers. At least get started with one of these examples, unless what you're working on is not part of this. So the step number one, or I should say option number one, is Python omitive example. And select this for most image processing tasks using Python, unless you plan on doing machine learning using GPU, in which case, obviously, use the second one. You can also create ImageJ scripts and use the ImageJ example. Please go ahead and create this to see how the structure looks like if you really want to work with ImageJ. Of course, we do have MATLAB, Java, and a quick Python Hello World example. So let's pick Python omitive example. And by the way, OME-TIFF stands for Open Microscopy Environment TIFF file. This is nothing but a TIFF file with an embedded XML that contains all the relevant metadata. So if you're working with proprietary images, for example, with Zeiss images, the file format is CZI. So it contains all the metadata. So when you convert that into omitive, the metadata gets saved into an XML file that's embedded part of this TIFF file. Okay, then we tend to use this as a standard input and output image format for most of our modules, especially all the modules that deal with image processing on APEER.com. So go ahead and create now. And now it's going to copy all the files from this cookie cutter template into your new module. Okay, so scroll up here. You can see that the build status is initializing. A build will soon be triggered. Pretty soon it changes to build status is running, and then wait until the build status is finished. Okay, let's just give it a couple more minutes. You see a build is currently running, and I'll explain what this is in a minute when we actually build our own module. Okay, now that the build is succeeded, now I can go ahead and proceed with these steps given down here. Okay, and again, the prerequisites, we already talked about it. Okay, Git, and if you would like to test your modules locally on your system, then you need to have Docker. I installed Docker for Windows. And step number one, copy the code to your local drive. So I'm going to copy this, and of course, if you forget your credentials, like Git credentials, you can always provide them here again. Okay, hopefully I remember mine, so I'm going to copy this, and now you can go to your Windows command prompt, or in my case, I'm working on Windows 10, so I'm going to use Windows PowerShell, which is like command prompt, but I like this better. Okay, and navigate to the right folder. Of course, you probably know how to navigate, right? CD, go to CD. In my case, it's called module demo. That's the directory I am under. And now go ahead and paste this. So all we are doing is git clone and that address where the code is residing. I'm going to hit return or enter. And it should come back asking me to enter my username. And let me enter my username and the password for Git. So now it should be copying all the files, and if I open the directory right here, let me change the icons back to somewhat smaller. Now you see that I used to have this Python file and of course my Mona Lisa noisy and NLM. Now it added a new directory called NLM_denoising and whatever that extension is. So now when I go ahead and open this, you should see a few files in here, and let's edit a couple of these files to convert this default cookie cutter module into a non-local means denoising module or application. But first of all, let's actually have a look at what files do we have in this directory. Yeah. So if you look at input, let me double click on input. Now you should see a couple of files. These are the test input files that gets downloaded or copied, from the cookie cutter template, and they're pretty good files to use for testing purposes. One is a JPEG file, and the other one is OME-TIFF, because probably you do not have an OME-TIFF file for testing. So please go ahead and use those. Now the git and git ignore, these get created because as part of the git, and these are the tracking files, because whenever you make any changes, these are the files that are monitoring these changes. Now APEER main.py, in fact, let's go ahead and open that file to see what's inside APEER main.py. Let me go ahead and zoom in, and as you can see, there are a couple of libraries that are being imported, and then where the inputs are coming from, where the outputs are coming from. We'll edit a little thing. Again, these are only like 8-9 lines of code, right? So there is not much to look at this yet. So we'll get back to this. And Docker file, again, Docker file contains a few lines of code, or instructions, I should say. In fact, let's go ahead and look at it. Docker file contains a few lines of instructions. The first line indicates the base image, Docker image, upon which this entire Docker is going to be built. So this second line here that you see is the working directory inside this Docker container, or the Docker virtual environment. And the next line is what files to copy from the local drive to the Docker. And the next line is installing whatever is inside this requirements.txt, and a few more files to be copied. We'll get back to this, so that's why I'm going a bit fast. And the next line is, okay, the entry point is, okay, type Python space APEER main.py to run this Docker, okay? And APEER main.py is the main file that we actually looked at a second ago. So here, this is the APEER main.py. All it's doing is importing this geometric transformation file, which we'll see next, right there, geometric transformation. This is the main Python file. So for us, this would be the non-local means file that we just created a minute ago here. NLM2D working, that's the file that I'm going to copy in here, or I can edit geometric transformation.py, either way. Module specification.json, this is the file that describes the user interface of your module on APEER. Because on APEER, your module may have some user interface, right? So if this is a non-local means denoising, actually let's get back to the code. If this is non-local means denoising, obviously it doesn't make sense to for example, hard code the patch size and patch distance, because a different patch code or patch size or patch distance would work better on different images. So maybe you would like the user to provide these patch size and patch distance so via a user interface. So this JSON file here, module specification.json, contains the information on building this user interface. Okay, we'll get to that in a second. And README is README, and requirements.txt contains basically here you can see it's just names of like 5 different libraries: APEER devkit, APEER omitif, scikit-image, scipy, and numpy. And these are the packages that need to be installed because these our code is dependent. For example, we need to install numpy, we need to install scikit-image, because of course we are importing these libraries to make our code work. Okay, so now that we looked at exactly what the files mean, now let's go ahead and start editing them to make sure it works for our code. First step, let's actually go to geometric transformation.py and have a look at it. The default Python function, or the default code here for this module, it's very simple. All it's doing is, as the name suggests, geometric transformation. So it takes an input image. Oh, sorry, I didn't mean to edit it. It takes an input image, and the user can provide angle by which the image needs to be rotated, shift in X and shift in Y. So these are the input parameters for this function, geometric transformation. And then these lines are basically implementing whatever this function. Taking the input parameters and then applying those to shift or rotate the image. And it's returning the image rotated, or the rotated image. Okay, that's as simple as it is. And then at the top, we are defining another function to execute by taking these inputs. Okay, and then the next few lines are, again, I don't change a lot here. Again, I'll show you exactly what I'm going to change. The first part is, if the image file is an omitif image, okay, then do this bottom part, which is convert that image into an 5D array and apply that to each 2D slice by apply this function to each 2D slice. In this example, this is geometric transformation. As you can imagine, as you probably guessed, we are going to change this geometric transformation into non-local means in a minute. Okay, So this is what our agenda is. So let's go ahead and define a new function. In fact, let's create some space here, and let's copy and paste our code and then edit the code down here. Okay, so I'm going to create some space, and I'm going to copy the code from my NLM 2D and copy this part, okay, and paste it over here. And of course, I need to make sure that I have all of these imported as part of my new file. Okay, so from sk image restoration, okay, we are importing those, and we are importing these, and sk image import IO. I mean, I can probably delete this because we already have IO over there, and import numpy as np is already called up there. So I'm gonna delete those two lines. Everything else hopefully makes sense. Now, I just copied this, but I need to define all of this code as a function. So define, and I'm gonna call this NLM, okay? And this is the function, and what parameters do we need as part of this function. So I'm going to look at this geometric transformation for inspiration. So here I'm going to just do image 2D because I'm going to call my array as image 2D. And what other things do I want to parameterize? Maybe patch size. This is what I want users to actually provide, and also patch distance. These are the two things I would like the user to provide via the user interface. So let's continue defining this function. So now, of course, I do not want to read, I do not want to read a predefined image, right? We don't want to read this Mona Lisa noisy. So I'm going to delete all of this, and I'm going to just say image 2D. That's it. Okay. So there, because that's where this image is coming from, right? So image 2D as floating point 32. So that's it. So my image is image as float 2D, and let's also add a tab to our sigma and to our print statement. Let's go ahead and print while it's doing. So I'm just making sure all this code is part of this function that I'm defining, which means they all need to be tabbed. So here we have image 2D, okay, and sorry, let me go ahead and call this my image 2D equals to image as float sigma estimated. Now let's actually go through each line. So here I no longer have an image, I have image 2D. So let's go ahead and do that. And finally down here also I have image 2D, and my patch size is not equals to 10. It is equal to patch size because it's coming from the user input up there. Same with my patch distance, okay? Same with my patch distance. Everything else I'm going to leave pretty much the same. Denoise image, and of course we are not saving the image. What does a function do here? It returns something. So I'm going to return denoise image as, that's a long name, I should have used a shorter name, but this is fine. Okay, so there you go. So now we have our new function ready. A couple more things to edit and we should be done. If you look down here, it says test code locally. If name equals to main, then it's going to execute the code locally, meaning if I run it right now. So it's a good way of doing your sanity check. Right now, it's actually looking at the folder input, and inside input, it executes these two, right? So if you want, you can actually copy the Mona Lisa noisy. For example, let me go ahead and copy that inside my input file or whatever input file that you would like to test. And I'm going to just, instead of the other one, I'm going to replace this nucleotubulin to my Mona Lisa noisy.jpg. Okay. Since I do not have Mona Lisa omitif, I'm going to leave the other one as is. This enables me, allows me to check how it works on omitif file. Now, I do not have three inputs, right? We don't have this. So here you have angle, translation in X, and translation in Y. In our case, we have patch size and patch distance. So I'm going to just say 3 and 5. Okay, same thing for these, 3 and 5. So all I'm doing is editing the existing geometric transformation code, and then I'll rename the file later to nlm.py or something else. So for now, let's leave this file name as is. Okay. So we're done with this bottom part, and we have our function defined already. So let's go ahead and edit the top input side to make sure everything makes sense. So execute image path. Again, we do not have angle, shift X and shift Y. We have patch size and patch distance. Okay. And I'm coming down here, and everything looks okay, and 5D and image path. And now the function that we are actually going to call is not geometric transformation here, it is NLM. Okay, array 5D, there is no angle, patch size equals patch size, and same thing with patch distance. Okay, and we do not have any other inputs, so let's go ahead and close this. Okay, so there you go. So that part is done. Let's keep going down. Okay, and array out, array out. I'm just going to look for anything that says geometric transformation and change it. So let me create a bit more room so we can see what's going on here. Okay, so instead of geometric transformation, again, our function is called NLM, and we do not have these. So patch size and patch distance. There you go. I think we are all set, and I'm not going to delete this geometric transformation function. I'm just not going to call it up here, right? So it can stay there. If that's bothering you, you can go ahead and delete it. So one final sanity check, I'm just going to go through this and make sure everything makes sense, and then we are done with this file. That's it. So at this time, if we want, we can actually check this code locally, or run this code as Python locally. Remember the last lines here, test code locally. So let's actually comment this part out and change the parameters of my Mona Lisa noisy to the ones from our original file 10 and 3 to make sure we get whatever we got earlier, 0.0696, right? So let's change my patch size to 10 and patch distance to 3, and let's go ahead and run this. Well, that's different than what we had there, and also we have three numbers here, 0.071, 0.07, and 0.0715. So the reason that we have three is because if we go back up and look at the code, it says, okay, if it is omissive, do something, right? If it's not omissive, what does it do? It checks for a number of dimensions. If it is 3, this is a color picture, right? This is an RGB image. So if it is 3, then it's going to apply the function to each channel that we have here. So it's going to, in this example, it looks like it did, red, green, and blue separately. But if I go back in my folder, now I should see an additional file called Mona Lisa outside here, yeah? And then if I open, this should be the cleaned image, or denoised image, I should say. So there you go. So this is our denoised image, which looks very good. And inside my input, I have my noisy image, which is, as the name suggests, well, this is our original input image. So this is the noisy image. So now we tested that, or let me minimize this. Now we tested that our geometric transformation.py, which we changed it to perform non-local means denoising, is working great. Okay, so let me go ahead and close it. And first thing first, let me go into this our input folder and change the file name of geometric transformation to nlm.py. Okay, so now that I'm done with that, let's actually go back and open APEER main.py. Okay, so here a couple of things to change. Again, so far all we have done is changed the default geometric transformation file, and instead of importing the geometric transformation.py, I'm going to import NLM. Yeah, that's the only one thing I'm going to change up here. And the other thing I would like to change is, of course, replace the geometric transformation with NLM. and input image is okay, input image, and the other input that is coming from external input is patch size. Okay, and again, you can read the documentation on APEER. Everything is explained over there, but I'm just going to make sure this patch distance, and we can delete this last part. So if I expand this side, let's go ahead and delete the shift Y. We don't have that input. There you go. So we are all set. So we have that. This is the only thing I'm going to change in APEER.py. So one, we changed our Python file name from geometric transformation to NLM. So that's one thing. And then the inputs. Everything else is taken care of by APEER dev kit. By the way, you can go to GitHub and get more documentation about this. If you know how to, if you're an advanced programmer, you'll probably appreciate the effort that our guys actually put in there. So it's using this dev kit the way we define our inputs has become easy. Okay, so input image, patch size, and patch distance. I'm done with APEER main.py. The next thing I would do is change the Docker file. Okay, so let me go ahead and drag the Docker file here. This is nothing but a text file. Okay, let me zoom in so you can actually see what I have in Docker file. The first line from Python 3.6, this is the base image upon which we are going to build this Docker. So I'm going to leave that as it is because I'm still using Python. Python 3.6 actually works great. My working directory inside the Docker container is user src app. I am okay with that. And then it copies requirements.txt. Now let's actually open our requirements.txt file, this text file that actually contains, sorry, let me drag it here, that actually contains all the libraries that are needed for our Python code to actually work. So I'm going to leave everything as is. APEER devkit, APEER omitif, scikit image is fine, scipy is fine, numpy is also okay because I think scikit image numpy. So there is nothing else we need to import in addition to what has already been. I mean, this is basically defined in the default file anyhow. So I'm not going to change any of that. Sometimes when you're building this Docker, when things fail, oftentimes that's because you have this a specific version number, and the reason for having this version number is to make sure that Docker actually works even 5 years from now. Okay, because if new version of numpy actually comes up or new version of scipy, then whatever you have written is probably not compatible for future, right? So that's why we want to lock it. But sometimes I've seen this fail, so you play with these version numbers to make sure it's actually working fine. So requirements.txt, I'm gonna leave it as is. And let's go back to our Docker file. And in the Docker file, it's copying requirements.txt to this working directory. Okay, and once it's copied, what it's going to do, it's going to run pip install all of these libraries that we defined in requirements.txt. That's all. Okay, and then it's also going to copy APEER main.py. So that's fine. I do not want to copy geometric transformation because we don't have that. We have nlm.py. Also copy module specification.json, which is great. Everything else is fine. So if you look at this, the only thing I've changed is change the file name from geometric transformation to nlm.py. That's pretty much it. Okay, I'm going to go ahead and save this file and move on to the next thing. Module specification.json. I'll get to this in a second. So let's skip that for now. Mona Lisa noisy.jpg is the file we just created. We can go ahead and delete it. During our testing process, we created that. nlm.py, we already worked on it. Readme, not much in there. I mean, you can go ahead and read that. And requirements.txt, we already looked at this. So we are pretty much done with our module, except for this JSON file that actually, in fact, let me open it. If you know how to work with JSON files, go ahead and work with this. It's basically telling you that, okay, the inputs are input image, angle, which is type of integer, shift x, which is an integer, shift y, which is an integer, and my output is an output file. So that is my inputs and output specification. For a user interface, input image, okay, and angle is coming from the user input, and the widget that it's going to use is a slider, which means the user is going to slide to define what the angle is. Here the widget is a text box. The user is going to type. So how do you know all of this? Of course we have documentation, but more importantly, APEER made it easy to, let's go back to this. So where were we? We were copy code to local drive. Step number 2, generate specification, right? So here you can actually generate this specification file with much ease, okay? And here is how you can do it. Okay, step number 1, add an input. Our input name, if you remember, again, you can go back and look at the nlm.py code, and let me zoom in again. If you remember, our input image is actually, where is my APEER? Sorry about that. APEER main.py. Okay, so these are the inputs that are actually coming in. The input number 1 is input underscore image. So I'm going to copy that name. I want to make sure I get the name correct. Okay, this is very important. And input description, you can just say provide input image as OME TIFF or TIFF or JPEG or PNG, whatever. I mean, this is basically a bunch of text, and input type is file, right? So this is a file, that's an input, and this is an image file. And now we can say, is it accepted file formats? OME TIFF, TIFF, PNG, and JPEG are the accepted file formats. The one I did not select is CZI file. Okay, we need to convert CZI to OME TIFF first. So there you go. So that's input number 1. Now I'm going to add another input, and this input, again, what did we call this? Patch underscore size. So let's just call this patch size, and enter patch size as an integer, for example. Okay, enter patch size as an integer, and this is going to be an integer, and text box widget is okay. Okay, so the user can actually enter text, and here I'm going to enter a default value over there, value of 3. Minimum value, I'm going to just say 3. Default 3 is fine. Maximum, let's just say 15. Okay, so this is my input 1 patch size. Another one, input 2, again patch distance. Okay, and again, same thing. It's an integer, it's a text box is fine, and default value of, let's put 5 here, minimum value 3, and let's put maximum value of 15. Okay, so, and also now let's add an output, and what is the name of our output here? Again, output underscore image. Okay, so let's go back, and there you go. Output image in the same format as input image. Okay, and this is a file, and again this is an image, and OME TIFF, TIFF, PNG, and JPEG. Set requirements, and there you go. This is how our module is going to look like. So you have input image, patch size, patch distance, output image, and we are not going to use GPU because we are not using TensorFlow or any of those. And then just click download, and this creates the JSON file for you. If you know how to do it, fine. Otherwise, this is a great tool, as you can see. So let's open the file to see how it looks like. So it's in my downloads folder. So let me go ahead, click and drag here, and there you go. This is how it looks like. So inputs, I have input image as input number 1, and patch size as my input number 2 with minimum and maximum, patch distance as my input number 3, minimum and maximum, and default values defined there, and outputs there. And how is my user interface going to look like? It's I mean, as you can see, for patch size, for example, the description is going to be here, and the widget is a text box, and so on. So there you go. So that's all we need. And now I am going to open my folder there and copy the module specification file that I downloaded. Replace the file and destination is okay, and module specification is also ready. So we are done with editing all the files here. So let's actually look at what our next step is by going back to APEER and module code. Adapt the code to your needs, which we just did, and test the module locally. This is a great way, you know. So you can actually download the APEER module debugger from this link here. Of course, if you know how to type the command in your Windows command prompt, you can go ahead and run the Docker. But the best way to do is go ahead and download this module debugger. And I'm going to open that. So let me open this module debugger, and you can see how easy it is to run this locally as a Docker file. Okay, so here is the module debugger. Let me open the folder. Again, looks like it's going to open it on my other monitor. So let me go ahead and bring it here. So sorry about that. There you go. And now let me go ahead and select this folder. This is my module folder. Okay. And I'm going to click on build, and it's going to build. And the first time may be a bit slow because it needs to download all the Python and needs to pip install all the dependent libraries and everything. So at the end of this, it's going to say either it's passed or it failed. If it failed, it's going to tell you exactly why it failed. Like, okay, the certain library is not available or whatever the reason is. Okay, there you go. Module successfully built. That's a great sign. So the next step is let's go ahead and run this this module. So let's go ahead and choose the file. And here is the input file, Mona Lisa Noisy. Let's open it. Path size, let's change this to 10 and 3 like what we have used earlier. Go ahead and run it. Okay, so there you go. That's a successful run of this module, and you see the same numbers show up here for red, green, and blue channels that you know that it's running fine. So the module is working great locally. Now I can just push it into the cloud and no surprises there. It should actually work exactly how it worked locally. And again, what we have done right now is initially we checked this Python file as a Python file. And we copied the code into this geometric transformation or the default Python file as a, and then we created a function out of it. And under these conditions, we actually ran this one more time to make sure it's working fine. And it is indeed, it was working great. So again, as a Python file. Now, finally here, what we just did is we built a Docker image when we did this build, and then when you run it, it's actually running the Docker container. So it's now working as a Docker container, which means the program or the application is portable. And let's go ahead and push it to the cloud and see it in action on APEER.com. So let me close out of this module debugger and go to APEER.com. Step number 5. Push the code. And how do we push it? First of all, git add all. Okay, let me go ahead and copy this, and I'm going to open my Windows PowerShell or Windows command prompt if you want. And let's clear the busy screen, and I'm going to navigate into this folder. Okay, NLM denoising, and I'm going to paste git add all. So this is adding all the files into my git, and then I have to git commit. Again, you can go back and check if you want. Git commit -m, and you can just give some message. Let me go ahead and paste it, and that some message can be my first module, and then go ahead and do that, and git commit again. Added all these 7 files. I mean, it's basically telling me that 7 files changed. And this is what changed with with all these files and everything since the last commit. Okay, so it's a good way sanity check there, and that's it. We are all set to do git push, right? So git and push. Let's go ahead and do git push, and as soon as you do that, it's probably going to ask you for your username and password, so only you can do this. Okay, so total 11. It actually pushed everything to the cloud. So if I go back up here, any second now it's going to say build status building, okay, from succeeded. There you go. It's currently running because it automatically recognized that, okay, a new push has happened, so it automatically starts running this. So Hopefully no surprises here, because we know that it actually ran very well on when we tested it locally, so it should hopefully work very well once it pushed to the cloud. There you go, the build succeeded. So now we need to make sure it's working fine on the platform, and the best way to do that is by creating a workflow. Okay, and let's give my NLM module for the, my NLM workflow. Create now, and the workflow will be created with this module. Okay, now let's go ahead and connect the input from our workflow input to the NLM denoising. And by the way, you can add another module after this to perform a different task, and another one after that to perform different task, and this is how you can create workflows. But let's make sure this is working and define my input file. If it's not already on the platform, let's go ahead and pull this monalisa.noisy.jpg, and it's going to upload it, and there you go. And you can upload, or you can actually select any number of images for a given workflow. This is how you actually do batch processing. So there you go. And the second here, remember, this is the user interface we created: patch size and patch distance. The default values were 3 and 5, and of course if you want to change it, you can go ahead and change it here. Okay, so 10 and 3. I'm going to go ahead and run it and look at the result. There you go, the workflow finished successfully. So let's click on see results. It takes us to the results page where we can look at this output. That's a cleaned image of Mona Lisa, and that is working great. And the results of every module are stored, so you can download this image, you can visualize this image using the online viewer, and so on. So this is how you build a module using your own Python code. Well, when I say a module, this is nothing but a Docker container, and run it on APEER platform. And now you can connect your module to other modules to create a workflow for your customized application. So I hope you found this tutorial to be very educational, and of course if you have any questions, you can always come down to contact us on APEER.com and contact our team if you need any help, or if you have any questions, or if you have some plain appreciation to the platform. Thank you very much for your attention.